it's all getting it. I feel like it gives me an air of real authority. Yeah, exactly. Yeah, exactly. Right. So today we're just going to go through examples using the general method for structures. Um, and for homework, we're just going to start getting into a lot of those kind of problems. It takes a while to make sense out of this, but once you've done a lot of them, they all start to sort of feel the same. That's kind of what you want, where you want to get to. Okay, so let's say we have a fixed joint. And then sort of a figure 4 shape. Those are all connected by pin joints. And let's say we have a downward force here of 500 newtons. And what do we want to do here? Say a horizontal force here of 500 newtons. And say those are each a meter. Say those are each, say those are a meter too. And so if those are each, so if this is half a meter, these are about 45 degrees. So this length would be square root of 2, like square root of 2 over 2, is that right? What? Oh, each is 1. Okay, so that's square root of 2. So this length is 1.4142, whatever. I don't know why I have so many decimal places. And let's say that the masses, so I'm going to number these eventually. The vertical one is 1, horizontal is 2, diagonal one is 3. Let's say that the mass of 1 is 10 kilograms. Mass of 2 is 10 kilograms. And the mass of 3 is 5 kilograms. What are the external loads on each member? Okay, so one by one, we're just going to isolate these members. So I'll start with body 1. There's a weight force that's 10 kilograms times 9.81, so 98.1 newtons. Down at the ground, that's a fixed joint, so what kind of loads do we have there? It can't move at all, so and it's a 2D problem, so both degrees of freedom in translation are eliminated, so there's a force vector. And then the rotational degree of freedom is eliminated, so there's a couple. Okay. That's the way to think about that. And now there's contact here with member 2. So that looks like an angle. It's not so this is the force on 1 by 2. And then up at the top, there's contact with member 3. So that's the force on 1 by 3. Any questions about that? And then row, question? Yeah. Okay, so I'm going to put the about point down here at the ground. So first for that force RA, there's no row vector. Force is RAX, RAY, and then no moment. And then the couple MA, we don't care about either of these, and that just applies a moment MA. Then the weight force is at 0, +1. The force is 0, -98.1, and there's no cross product. And then the force F12 has the same row vector as the weight because it's at the same point. And the force is F12X, F12Y. And the cross product is negative F12X. And the last one is the force F13. The row vector is 0, 2. The force is F13X, F13Y. And the cross product is negative 2, F13X. So now we can add up all the force vectors and set them equal to 0. I guess I'll write that all out as Newton's second law before I get to the equations. As soon as you start to get the flow of this and whatever, you can just go right into building your list of equations. But you don't have to do that. I mean, I think I always try to give you enough time that you can do this stuff in as many steps as you want. So RAX, RAY plus 0, -98.1 plus F12X, F12Y plus F13X, F13Y is equal to zeros. And then the moment equation, this should just say 0. Okay, so we have MA minus F12X minus 2F13X is equal to 0. And we can write out our first 3 equations. Our first one says RAX plus F12X plus F13X is equal to 0. The second one says RAY plus F12y plus F13y is equal to positive 98.1. And the third equation says MA minus F12x minus 2 F13x is equal to 0. So right now we have a list of 3 equations. How many variables? 1, 2, 3, 4, 5, 6, 7. Those are RA, F12, F13, and MA. So we can't solve anything yet. Thank you. One mistake like that messes up the answer of every single one. Okay, so now we're going to do the free body diagram of member 2. That's the horizontal one. There's a weight force here of 10 times 9.81. There's a downward force of 500 at the left end. At the middle, member 2 makes contact with 1. So that's F21, but we already have F12, so I'm going to write this as negative F12. One thing that can sort of help you with your bookkeeping is if you go through the members in order, member 1, then member 2, then member 3, and anytime you get to subscripts with where the bigger number is first, you already have the flip of that. So you can use Newton's third law. So like F21 means you've already done F12. F31 means you've already done F13. Okay, and that always is true. And then the last one, well, there's 2 more, I guess. So over at the right end, first there's a 500 Newton force applied at the pin. What member are we lumping the pin in with? 2. It's the lowest numbered member at that joint, so that's a 500 Newton force applied to 2. And we won't apply it to 3 when we isolate that. And then we also have contact between 3 and 2. So over here we have the force on 2 by 3 and a horizontal force of 500. Any questions about that? I guess I'll do the about point at the center. So the 500 Newton vertical force, the 0, negative 500, has a row vector of negative 1, 0. That's the vector from the about point to the point. The force vector is 0, negative 500. And the cross product is 500. Then the negative F12 force has a row vector of 0. a force of negative F12x, negative F12y, zero cross product. And the weight force, the row vector is 0. The force is 0, negative 98.1. Cross is 0. Then F23, the row vector is 1, 0. Force is F23x, F23y. Cross product is F23y. And then the last one is the horizontal force. The row vector is 1, 0. The force is 500, 0. And there's no cross product. Well, think of it this way. So the system, and this is actually, I think, a helpful way to think of systems of equations. And a lot of times, if you're thinking like, oh, can I use a new coordinate system? Or all we're trying to do is come up with a system of equations, every one of which is true. Okay. And if we're treating this as a rigid body, we can use, we can put the about point wherever we want and the equations will be true. So we can do it in this case too. You do have to be very careful. Like I would not recommend ever changing the orientation of the coordinate system because then the components mean different things. But really, technically, you can do that too. You just have to, when they show up in different equations, you have to make sure that they're represented in the same coordinate system. Okay. So we're going to do Newton's second law and the moment equation. But I'm just going to add up the x components in the force column, move any constants over to the other side. So we have 0 minus F12x plus 0 plus F23x is equal to negative 500. That's equation 4. It's a negative because, okay. And then the y components, we'll get that 500 at the end. So we have negative F12y. We'll get that 98 at the end, plus F23y is equal to, the constants add up to, negative 598.1. Move them to the other side and you get 598.1. Like I said, feel free to write out Newton's law and the moment equation. It just saves a little writing if you see it or when you eventually have done enough of these that you're tired of writing all that. And then the sixth equation, we have 500 plus F23y is equal to 0. So F23y is equal to negative 500. Okay, so now we have 6 equations and variables. What did we introduce that's new? The only things we introduced that are new are F23, X and Y. We had 7 variables before, so now we have 9. Those are F12, F13, RA, F23, and MA. 2, 4, 6, 8, 9. And then the diagonal member, number 3. There's a weight force acting at the middle. That's 5 times 9.81, so 49.05. Up top, member 3 is in contact with member 1. So that's F31, which is equal to negative F13. We know we have F13 because if the subscripts have the bigger number first, you've already seen the opposite version. So I'll call this negative F13. And then down at the other end, we have to think again about what we're associating the pin with. We decided to associate the pin with member 2, so that 500 Newton force is applied to member 2, not 3. And so the only thing we have here for 3 is the force on 3 by 2. And so that's negative F23. Okay? And then rho, force, moment. Let's see. I'll put the about point here, I guess. So the first force I'll do is negative F23. The rho vector is 0. Force is negative F23x, negative F23y. Moment is 0. Then the weight force. The rho vector is negative 0.5, positive 0.5. The weight is 0, negative 49.05. The cross product is 24.525. And then the last force is negative F13. The rho vector is negative 1, 1. The force is negative F13x, negative F13y. And the cross product, is F13y plus F13x. So equation 7 says negative F23x minus F13x is equal to 0. Equation 8 says negative F23y minus F13Y is equal to positive 49.05. And equation 9 says F13X plus F13Y is equal to negative 24.525. 9 equations. We didn't add any new equations this time, so there are 9 variables, and we're out of bodies to analyze right at the right time. So now, well, will you just fill out this matrix and calculate it and get back to me, and then I'm going to pause this so it looks like, can I see your calculator for a second? Let me just. Put one up here that I want you to work on, but just sort of like we'll go through it step by step. Okay, so let's say that we have 2 members connected to the wall by pin joints. They're connected to each other by a pin joint. So this is an isosceles triangle. The lengths are the same and the angles are the same. Let's make that 1 meter. And let's say that those angles are 5 degrees. And let's, at the joint, apply a force of 1,000 newtons horizontally. And we'll neglect the weight. What are the external loads on each member? Yeah. Five. Okay, so just so that we do it all the same, let's call the top one member 1 and the bottom one member 2. And let's start out with free body diagrams of each one. So draw the free body diagrams of each one, and then I'll go through it, and then we'll go through the calculation. So for member 1, up at the top, that's a pin joint. So I'll call that RA. And then at the bottom, at that joint, we're assuming that the pin is part of member 1 because that's the lowest numbered member. So we have the force on 1 by 2. And we also have this horizontal force of 1,000. And then for member 2, down at the bottom, that's a pin joint connecting it to the wall. So I'll call that RB. And then at the pin in the middle, that pin is not part of member 2. It's part of member 1. And so that 1,000 Newton force is only applied to member 1. All we have going on here is the force on 2 by 1, or negative F12. Oh, yeah. Any questions about that? Okay, so before we start going into calculations, when we come up with the external loads on each of these members, do we know anything about the directions of those loads? We do, and this is just something I'm trying to start you getting used to looking for. Each of these is just a 2-force member. Okay? There's no weight, and each one we just have a force vector at the top and at the bottom. Okay, so 2 force vectors on each one. Even though here, the force vector is broken up into 2 separate things, that's still just 1 force vector. They're happening at the same point, so you can add them together. Okay, and anytime you have a structure where all your bodies are just 2 force members, we know that it's either in pure tension or pure compression. That's all it can be. Okay. Have I said that before? Oh, shoot. It's deform I was saying that in. Okay. So it's called a truss. And we'll talk about how to do simplifications with those kind of things in the future. But so each one of these, when we do the calculations, are either going to have equal and opposite forces acting away from each other, or equal and opposite forces acting towards each other. In this case, you can probably intuitively tell that they're both going to be in tension. And then and so, we'll have, say, 500 going that way, 500 going that way or something. Based on this configuration, does anybody have a sense of how big those tension values are going to be? This is actually sort of a cool example, I think. These tension values are going to be ginormous. Way bigger than 1,000. And that's the way it works anytime so you can create a big tension in a cable by applying a force, like have a cable almost horizontal and press down on it. You can create a big tension that way. And the same thing here. If you get these things almost perpendicular to the force that's applied, you can get these really big forces by applying small forces. All right. So now, just with member 1, go through the Newton's laws and come up with 3 equations for member 1, and then I'll go through it, okay? Okay, so rho, force, moment. So I'll start out with the force F12, yikes. Rho vector is 0. Force is F12 x and y. And the moment is 0. And then the 1,000. The rho vector is 0. Force is 1,000, 0. Cross product 0. And then up at the top, what are the cosine and sine of 5 degrees? Point 996. And the force vector is Rx, Ry. So the cross product is negative 0.087 Ry minus 0.996 Rx. And so our first equation says F12x plus Rx is negative 1,000. Our second equation says F12y plus Ry is equal to 0. And our third equation says negative 0.996 Rx minus 0.087 Ry is equal to 0. And there are 4 variables there, so we can't solve it. And now do the same thing, go through get the equations for member 2. Okay, so now we have 6 equations for 6 variables. And is anyone already working on solving this? Let me know when you have answers. Okay, yep, I'm ready. Okay, 7.6 and 86.7. Okay, 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 good. All right, so now let's put these into free body diagrams and see what the external loads are on these members. So first we have member 1. Up at the top, we have this force negative 992.4, 86.7. That That can't be right. Let's see. Okay, that's what we're looking for. What do you get? Okay, negative 500, negative 5,000 what? Okay. Better to me. That's more what I was looking for. 5724. Okay. Negative 500. Negative 5724. Okay. So now put this in the free body diagrams. And you get, so negative 500, positive 5724. And down here, you have two things acting on member one. You have F12, and you also have that force of 1,000, and those add up to a force of 500, 5724. And if you use, right angle trigonometry, right triangle trigonometry to figure out the angle that these forces are at, this one should be negative. The y component is negative. Over here, you have force of basically, right around 6,000, a little under 6,000 going this way. And here you have 6,000 going that way. Okay, so you get this really big tension, 6 times as big as the external force that's applied. And then for the other one, you have sort of the same story going on. You have negative 500, negative 5724, and up here you have negative F12, so that's positive 500, positive 5724. Again, those are tension exactly in line with that for 6,000 that way, 6,000 that way. Any questions about that?
You're saying then in the x-axis we have two forces that are,
Okay. So this is actually sort of a cool mechanism for machines or any, if you ever need to apply a really big force, a force so big that it would be hard to generate a force that big through your actuator or whatever, you can get a cable or a linkage set up almost perpendicular to the force you're going to apply. Apply that force, and you can imagine if you're trying to generate a big force on this pin, we just generated a 6,000 Newton force on that pin by applying 1,000 Newtons that way. The key thing is that these are nearly perpendicular to each other. The closer to perpendicular, the better. Okay, that's all. So on Thursday, maybe we'll do a example get in groups and do like an example at the board, and then we'll go on to the next topic, which is these two force members, how you can simplify it when you have trusses. Because, let me say one more thing about this. So I said that these, in these cases, both of those two members are two force members. And so I knew going into it that the forces were going to be along the length of the members. Well, if you know that going into it, there must be a way to take advantage of that. I mean, if you know the directions of those forces, then the X and Y components aren't independent of each other. And so that's what we're going to do when we develop this truss simplification. But you have to be very careful using it because it only works if all your members are two force members. Okay, that's all.